In 1861, a Scottish scientist named James Clerk Maxwell came up with an explanation to describe light. Now, when I say light, I don't just mean the kind of light that we see. I mean all kinds of light, all kinds of what we call electromagnetic radiation, or EMR. James Clerk Maxwell said that EMR is produced by accelerating charges. Now be careful here. We've talked about charges that are moving and what they generate before. We said that a stationary moving charge will generate a gravitational field and an electric field, but not a magnetic field. A moving electric charge will generate a gravitational field. It'll also generate an electric field, and it'll also generate a magnetic field. But if we have an accelerating charge, not just a charge that's moving, Maxwell's saying that a charge that is accelerating will generate a gravitational field and an electric field and a magnetic field. But these two fields, this electric field and the magnetic field, behave a little bit differently than the electric field and magnetic field produced by just a moving electric charge. I'll explain what I mean by that in a moment. For now, you can write this down. Accelerating charged particles generate changing magnetic fields. Changing magnetic fields, and changing electric fields for that matter. That word changing is important. Okay, again, it's going to become clear to you in a few moments why that word changing is important. But the bottom line is this, guys. If you have a stationary charge, it doesn't generate a magnetic field, period. It does generate an electric field, but not a magnetic field. If you have a moving electric charge moving at a constant speed, it will generate an electric field and it will generate a magnetic field, but not a changing electric and magnetic field. In order to get the changing electric and magnetic field, you need an accelerating charge, and this changing is important. In fact, we're going to say after we're done this section here, we're going to identify three really key words. Three words that if you remember these three key words, then you can remember the gist of this whole thing. That word changing is one of them. Okay, critical to this whole thing, the idea that it's a changing magnetic field and a changing electric field. Why is it so important? Well, because changing magnetic fields will generate changing electric fields. Think about what I just said there. Changing magnetic fields will generate changing electric fields. A magnetic field will not generate an electric field. A changing magnetic field will generate a changing electric field. And similarly, a changing electric field will generate a changing magnetic field. So this is the way that EMR works. You have an accelerating charge. The accelerating charge generates a changing electric field. I'm saying delta because I don't want to just say E with the arrow over it. It doesn't just generate an electric field, it generates a changing electric field. We'll call that electric field number 1. It also generates a changing magnetic field that we're going to call B2. But it's changing, so we'll stick a delta in front of it. The accelerating charge generates this. Now, this changing electric and changing magnetic field will generate this. See what I've done there? Changing electric field, number 1, generated a changing magnetic field. And a changing magnetic field generated a changing electric field. Changing magnetic field number 2 generates a changing electric field. And changing electric field number 2 generates a changing magnetic field. This is what EMR is. If you have a constant electric and magnetic field generated by a moving charge, that's great, but you don't have EMR because a constant electric and magnetic field wouldn't generate a new electric and magnetic field, which in turn wouldn't generate a new electric and magnetic field. You need an accelerating charge to generate this, the changing. And that's important because if you don't have this, then you don't have this. These first two electric and magnetic fields won't generate anything else. Yep, question? Yes, sorry, that should be B1, yes. Thank you. Well, there you go. That's how good the explanation was, that even when the diagram or the representation of it's wrong, you guys still get it. Good. What does this actually look like? Well, it's hard to draw, but I'll do my best here. The next page is probably a better diagram, but just bear with me on this one. Here's the y-axis. Here's the x-axis. Here's the z-axis. It's perpendicular to that. Let's say that this is electric field number 1 on the y-axis. This is magnetic field number 1. Does that make sense? So electric field number 1, and you've got magnetic field number 1. Notice something about these two fields. One, they're both sinusoidal, although it doesn't have to be sinusoidal. Usually it ends up being sinusoidal. 2, they're in phase with each other. That means if you have a crest of one wave, you have the crest of another wave. And 3, this word becomes really big throughout this unit as well. They're perpendicular to each other. Electric field number 1 is changing. So is magnetic field number 1. Electric field number 1 will generate this. Magnetic field number 2. And magnetic field number 1 will generate this. Electric field number 2. And so on, and so on, and so on. If you don't have the accelerating charge, you don't have the changing fields. And if you don't have the changing fields, then what you see right here, the first electric and magnetic field won't do anything. They won't generate the second electric and magnetic field. And if you don't generate the second and the third and the fourth electric and magnetic field, you don't have EMR. Here's a little summary of what we just said. EMR is energy, pure energy that travels in a wave-like form without the need for a medium. What does that mean, without the need for a medium? Yeah, it doesn't need something to travel in, something to transfer. Now, it doesn't mean that you can't have a medium. Visible light travels through space from the Earth to the, from the sun to the Earth. It takes about 8 minutes to get from the sun to the Earth. Completely through empty space, doesn't require a medium to go through. Now, having said that, when it reaches the Earth's atmosphere, it doesn't just stop. It travels through the Earth's atmosphere as well. It doesn't need the Earth's atmosphere, but it can travel through the Earth's atmosphere. EMR is energy that travels in a wave-like form without the need for a medium. It consists of changing electric and magnetic fields that are perpendicular to each other and that are caused by accelerating charged particles. Both of those waves travel perpendicular to each of them. So if electric is on X, magnetic is on Y, it travels on the Z axis. If the electric is on Y and magnetic is on Z, it travels on the X axis, and so on. And there's maybe a better representation of what it would look like. Electric field number 1, magnetic field number 1. Well, electric field number 1 will generate magnetic field number 2, which is this guy down here. And magnetic field number 1 will generate electric field number 2. But they'll only generate, electric field number 1 will only generate magnetic field number 2 if the electric field number 1 is changing. And magnetic field number 1 will only generate electric field number 2, I should say, if that magnetic field is changing. Constant fields, nothing. Changing fields generate more changing fields. That's why we need an accelerating charge, because we don't get changing fields with a charge moving at a constant speed. Listen, there's 3 words here that if you remember these 3 words, you can probably answer any question that comes up on this. 3 key words. Okay, three keywords always, or at least nearly always, lead you to whatever the answer to whatever question you have that's relevant to this. What's one of them? Perpendicular. Yep. Perpendicular. The waves are perpendicular to each other, and the waves are perpendicular to the direction of propagation, we call it, or the direction of movement of the wave. So perpendicular is critical here. Everything is perpendicular to each other. Wave 1 from wave 2, and wave 1 and 2 from the direction of propagation of the wave. What's another of the three keywords? Well, that's important, yeah, electric field. Like, you need to know that there's an electric field and a magnetic field there, but good. Accelerating. Accelerating is important because we need not just a charged particle, not just a moving charged particle, we need an accelerating charged particle, one that's changing speed, increasing in speed or decreasing in speed, or changing direction. An accelerating charged particle. Finally, what's the last important word here? I should say the last important word. There's lots of important words, right, Jacob? Like electric and magnetic were important. But the last critical word here for remembering the gist of what's going on here? Changing, yeah. So when you're studying this, I would focus on those three words. If you can remember those three words, then the rest of it will probably come to your mind, if you can remember those three words. An accelerating charged particle is necessary to produce a changing electric and magnetic field that are perpendicular to each other and perpendicular to the direction of propagation of the wave. So I'd remember it in those three words in that order. Accelerating charged particle is necessary to generate changing electric and magnetic fields, which is critical, so that we get this perpendicular electric and magnetic fields that travel perpendicular to both of those waves. Now let's talk about some properties of EMR that show that EMR is a wave. Maxwell said that it's a wave. In fact, he said that it's two waves, an electric field wave and a magnetic field wave that are perpendicular to each other. There are four properties of waves that are exhibited by EMR that show the wave nature of EMR. One of them that we talked about in Physics 20 is called diffraction. You guys remember what diffraction is? Almost. Diffraction is the spreading out of a wave. If I have an opening or a barrier, and I have a wave coming towards that opening or barrier like this, only part of it's going to go through the opening. But the part that goes through the opening after it ends up going through ends up spreading out like this. Okay, that's diffraction. The spreading out of a wave as it goes through an opening or around a barrier. That's a property of waves. That is clearly defined property of waves. But that property of waves is exhibited by EMR. EMR will diffract. Visible light, ultraviolet, all the other forms of EMR will diffract. They'll spread out as they go through an opening. Therefore, EMR is a wave. Right? If you've got a property of a wave that's demonstrated by EMR, then logically EMR must be a wave. Now here's the second property that we talked about in Physics 20, interference. Remember in Physics 20 we had a situation like this where, I don't know, maybe you had a crest of a wave that looked like this, and then another crest of a wave that looked like this, and they interfered to produce a bigger wave. Do you remember that? The interference pattern looked something like this. In that case, that's called constructive interference, by the way. Do you remember that? When two waves combine to form either a bigger wave, as they do in this case, or a smaller wave, when you have a crest and a trough, they produce a smaller wave. That's interference. It's a property of waves. That is a clearly defined property of waves. But EMR demonstrates this property. EMR exhibits this property. Therefore, EMR must be a wave, or at least two waves, an electric field wave and a magnetic field wave. The next one is called refraction. And Benton alluded to this earlier on. He didn't use the word, but he said the bending of a wave. That's what refraction is the bending of a wave. If you've got a boundary between two media, between two different materials, and a wave comes at the boundary like this and changes direction like this, that's called refraction. That happens when a wave goes from one medium to another because the speed of the wave changes. We'll talk about that in a lot more detail later on in this unit, early next week actually. It's a property of waves. It's a distinct, clearly defined property of waves, but it's exhibited by EMR. You've observed it before. You guys have probably all seen a picture of a pencil in water. The pencil looks to be bent. Why does it look to be bent? Because the light changed direction when it left the water-air boundary. Changed direction. If light changes direction, then light must be a wave. Because that change in direction or refraction is a property of waves. The fourth one, this is probably one that many of you have never heard of before. Certainly we did not cover this in Physics 20. The fourth one is called polarization. Polarization involves the filtering of components of waves. Let me give you an analogy to help you understand what this means here. I've got a piece of plywood. In a piece of plywood, I've got an opening or a slit in the middle cut out. It's vertically oriented. Now, if I put a rope through that opening, let's say Jacob is holding on to one end of the rope. Here's the piece of plywood right here with the vertical slit in it, and I'm holding on to the other side end of the rope on the other side of the plywood. Got it? So the plywood is in between us, vertical like this, okay, with that vertical slit where the rope is going through. Okay, if I cause a wave in that rope like this, a vertical wave in that rope, then the wave goes right through that opening and Jacob detects that wave, right? But if I make a horizontal wave like this, how much of that horizontal wave goes through that vertical opening? None. Yeah, none. We say that it's polarized vertically. We set up a polarizing filter to allow only one component of a wave through. In this case, it would be the vertical component of a wave. What if I had a wave, what if I produced a wave like this that was kind of diagonal? What would make it through that opening then? Part of it. The vertical part of it. The horizontal part of it wouldn't make it through. The vertical part of it would make it through. It's polarized vertically. It filters out all but one of the components of the waves. In this case, the vertical component. Does that make sense? If we had another polarizing filter, another piece of plywood with a vertical slit in it, so we got polarizing filter number 1, polarizing filter number 2, and we put them together, then it's not going to change anything, right? So there's Jacob, there's me. I've got both of those pieces of plywood in between us. Both of them are oriented vertically. When I fire the wave through vertically, it makes it through. When I fire it through horizontally, none of it makes it through. When I fire it through at an angle, kind of diagonally, only the vertical component makes it through. But if I change the orientation of this so that this one has a horizontal slit, and I put one in front of another, put that rope through the middle, fire a vertical wave through, does it make it through? No, because it's filtered out by this one. If I fire something that's horizontal through, does it make it through? No, it gets filtered out by this one. So now we would say that wave is completely polarized or totally polarized. It filters out everything. And that's what happened in the demonstration that you guys just did, where we turned the polarizing filter 90 degrees. One was horizontal, one was vertical, and it filtered out everything. Does that make sense? This is a property of waves. Polarization is a property of waves. But you saw with the demonstration that we just did that it is exhibited by or demonstrated by visible light, which is a form of electromagnetic radiation. Therefore, EMR, electromagnetic radiation, must be a wave. We will learn later on in this unit properties of EMR that are or properties of particles, I should say, that are exhibited by EMR. Evidence for the particle nature of EMR rather than the wave nature of EMR. But for now, These four wave properties demonstrate very, very well the wave nature of EMR. Last page of notes for the day here. It's kind of a big one, but it's the last one. This is going to show for us the 7 types of EMR that you saw in the EMR song that we played at the beginning of class. What were they? What was the first type?
Radio waves.
Radio waves. If we're ranking these in terms of frequency, from low frequency to high frequency, which also, by the way, corresponds to low energy to high energy, which also, by the way, corresponds from high wavelength to low frequency. Low frequency, low energy, high wavelength. Why is that the case? Remember in physics 20, we use this equation, V is equal to F times lambda. F is equal to V over lambda. F and lambda are inversely related to each other. As one goes up, the other goes down. So if we're starting with radio waves which have a low frequency, then we're starting with radio waves that have a low energy. We're starting with radio waves that have a high wavelength because it's opposite to frequency. What was the next one? Radio waves? Microwaves. Radio waves and microwaves I've grouped together here because radio waves and microwaves, although the exact mechanism by which they're generated varies slightly, it boils down to almost the same thing. They're both produced by accelerating charges, as is every type of EMR, but specifically radio waves and microwaves are produced by oscillating electric charge. What does that mean? Oscillating electric charge. Well, it means the electric charge that's going back and forth, back and forth, back and forth. It's oscillating back and forth. As an electric charge goes one way, it must speed up, then slow down, then stop. Speed up, slow down, stop. Change direction. Speed up, slow down, stop. Change direction, speed up, slow down, stop. As it speeds up and slows down and changes direction, it's accelerating and it's generating EMR. Very low frequency EMR, radio waves, or microwaves. What was the next type of EMR that was generated after microwaves? Infrared. Infrared, then comes visible light. I'm going to put this up here because we're going to break down visible light into 7 subcategories. They all have subcategories. We just don't usually identify the subcategories of anything but visible light. The reason we do identify visible light subcategories is because we can physically see these ones. What are they? Yeah, which are? Yep, somebody said it. Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. What comes after visible light? Ultraviolet. What does the word infra mean? What does the word infra mean? It means below. Where does infrared appear on the spectrum? Right below red. What does the word ultra mean? Ultra means above. Where does it appear?
Above red.
Right above violet. Infrared is below red. Ultraviolet is above violet in terms of frequency. So we've got radio waves, microwaves, infrared, visible light, ultraviolet. These 3 types which we grouped together are all produced by transitions of electrons from high to low levels in atoms. You guys may have learned a little bit about this in chemistry class before, maybe not. The Bohr model of the atom says that electrons exist on specific levels, 2 on the first level, 8 on the second level, and so on and so on and so on. Electrons can make transitions from one level to another. As they make a transition from a higher level to a lower level, they give off EMR, usually in one of these 3 forms. If it's a small transition, it tends to give off a small frequency or a small energy form of EMR, like infrared. But if it's a big transition, it gives off a higher frequency or higher energy EMR, like ultraviolet. So if you go from level 5 to level 4, it's probably going to be infrared. If you go from level 5 to level 1, it's probably going to be ultraviolet because it's a bigger transition, a more energetic transition. What was the next one? X-rays, which I should have color-coded this different because X-rays and gamma rays don't really fit together there.
The next one's gamma
X-rays are produced by rapidly decelerating. What does that mean? Decelerating, slowing down, rapidly decelerating electrons that are slowing down really, really quickly. So what happens in the medical office, the hospital, or the dentist's office when you're getting an X-ray? They accelerate electrons to crazy high speeds. Conservation of energy, EI equals EF. It's like a car going down a hill, right? Electric potential energy, QV, gets converted to kinetic energy in the electron, 1/2 mv squared. Gets them going really fast, 10 to the 6, 10 to the 7 meters per second. And then we smash that electron into a target, and it stops almost instantly. All that kinetic energy that it had has to go somewhere. The kinetic energy that the electron had was transformed into an X-ray. And that X-ray is released, and then somehow, I'm not sure how they do this exactly, but somehow they focus the X-ray to go through your teeth, or to go through your arm if they think you have a broken arm, or your collarbone, or whatever the case may be. So X-rays are produced by rapidly decelerating electrons. Finally, what's the last one? Gamma rays. Gamma rays are produced by nuclear decay. What do we mean by that, nuclear decay? Well, we're going to talk a lot more about nuclear decay in our next unit, as we will transitions of electrons. But specifically, we'll learn that nuclear decay involves transforming matter into energy. Now, how exactly that happens, we're going to leave that for now. But in a nuclear reaction, a radioactive decay reaction, or some kind of fission or fusion reaction, we can change matter, we can change mass into pure energy. And when we do that, gamma rays are produced. Gamma radiation is produced. So you do have to remember these 7 types of EMR, and you have to remember the order of them, and you have to remember how each of them are produced. Generally, we say they're all produced by accelerating charges. Need accelerating charges because accelerating charges produce changing electric and changing magnetic fields that are perpendicular to each other and perpendicular to the way the wave moves. Yep?
Can you turn energy into matter?
Yes, you can. Yes, you can. Again, we'll talk more about that energy matter thing in our last unit. Now, do you want the good news or bad news? I got both. I got good news, I got bad news. What do you want first?
Bad news.
You want the bad news first? Everybody always wants the bad news first. Okay, here's the bad news. There are 7 different types of EMR. You could be given any frequency or any wavelength or any energy, and you have to tell me what type of EMR that is. That's 21 different ranges of frequency, energy, and wavelength that you've got to be familiar with in order to identify what it is. Now, you want the good news?
It's on the formula sheet.
No.
That's not on the sheet.
It should be. It should be on the formula sheet, but it isn't. Here's the good news. The good news is that your teacher is not good at all at remembering things like that. If I had to memorize 21 different number ranges for frequency, wavelength, and energy, I would have no hope. If I had to do that, if we didn't have a little cheat for that, then I would honestly say to you guys, look, if you're not very good at remembering, you might just want to skip that, because you'd be investing hours for the possibility of one question. The good news is we don't have to. Okay, there's a little cheat that I've come up with that will allow us to only memorize 3 ranges instead of 21. I don't have a shortcut beyond that. Okay, but I think eliminating 18 different ranges that I have to memorize, I think that's okay. Here's what I want you to do. I don't see any way around this, so here's what I want you to do. I want you to memorize that microwaves have a frequency of 10 to the 9 to 10 to the 12 hertz. You got to memorize that. I'm not very good at memorizing things like this, but I can remember that. You got to memorize that X-rays have a frequency of 10 to the 17 to 10 to the 20 hertz. Again, I'm not very good at memorizing, but I'm good enough to memorize that. And finally, visible light has a frequency range of 4 times 10 to the 14 hertz to 7.5 times 10 to the 14 hertz. We're more specific with that one. Do you notice that? We didn't just say 10 to the 9, 10 to the 12, 10 to the 14, 10 to the 17, 10 to the 20. We identified a base, a very specific range. We did that because visible light is such a small band. Like, look at that. Microwaves go 10 to the 9 to 10 to the 12. The range is 10 to the 3. Same thing with X-rays. The range is 10 to the 3. The range of visible light is very, very small. It's very, very short. So we have to be pretty specific and put either side of it, either end of it there. Okay, look, if you can memorize those 3 sets of numbers, you are set for this. What if the question says, here's a frequency of, I don't know, 5 times 10 to the 14 hertz. What kind of EMR is it? Visible light. What if the question says the frequency of the EMR is 5 times 10 to the 18 hertz? What EMR is it? 5 times 10 to the 18 would be X-rays. What about 5 times 10 to the 11? Microwaves, good. Okay, we've got those 3 memorized, right? What if it's 5 times 10 to the 7? It's radio waves. We didn't have to memorize the radio wave range, right? We know that radio waves are below the microwaves. So as long as we've got microwaves memorized, why would we bother memorizing radio waves?
So what's the point of the other 18 then?
Sorry, I don't...
You said there's 18 other...
Okay, yeah, we'll get to that. We'll get to that. So if you've got 10 to the 8, then you know it can't be microwaves, so it must be by default radio waves. What if you have 5 times 10 to the 13? What is it?
Infrared.
You don't have to memorize the range of infrared. You just have to know microwaves ends at 10 to the 12, and visible light starts at 4 times 10 to the 14. And if it falls in between that, then it must be infrared. Same thing if you get 10 to the 15 hertz. Got to be ultraviolet. What if you get 3 times 10 to the 14? What is it? 3 times 10 to the 14. Infrared. What about 9 times 10 to the 14? Ultraviolet. 7 different ranges that we technically have to know, but really if we memorize 3 of them, we can figure out the other 4. Now, what if you're given a wavelength, though? What if you're given a wavelength? We haven't got any wavelengths memorized. Here's what I want you to do if you're given a wavelength. I want you to use this equation that you learned in Physics 20. V is equal to F times lambda. Rearrange it and solve for frequency. We get V over lambda. Replace a V with the letter C. V stands for any speed of any wave. C is specifically the speed of light in a vacuum, which is always going to be 3 times 10 to the 8 meters per second and is given to us on our data sheet. So what I want you to do is divide that 3 times 10 to the 8 by the wavelength that you were given, get a frequency, and then compare it against the 3 known ranges that you memorized. So for example, given the wavelength is 6 times 10 to the negative 7 meters, we would say the frequency is C over lambda, or 3 times 10 to the 8 meters per second, divided by 6 times 10 to the negative 7 meters, gives us a value of 5 times 10 to the 14 hertz. We haven't memorized what 6 times 10 to the negative 7 meters is, but we know 6 times 10 to the 7 meters corresponds to 5 times 10 to the 14, which we know falls right smack in the middle of, Jacob, visible light.
So it's 10 to the 8 meters per second.
Yeah. So you can imagine now how having 3 ranges memorized allows you to identify any frequency, but it now also allows you to identify any wavelength by converting wavelength to frequency. right? Now, the last one, energy. If you're given a particular energy, for now you're going to have to trust me that you can find the frequency in a similar way that we did from wavelength. You're not going to see that equation until a fair bit later in the unit, though. It's going to be probably 2 or 3 weeks before you see that equation. So for now, just know that you don't have to memorize 7 energy ranges. You will, in a couple of weeks, be able to calculate frequency from energy and then compare it against the 3 known frequency ranges. So, what have we learned today? The gist of what we learned today? Maxwell, accelerating charges generate changing electric and magnetic fields that are perpendicular to each other and to the way the wave moves. That's electromagnetic radiation. The 7 types of EMR: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. We also learned about the specific mechanisms by which each of them are produced. And we learned 3 frequency ranges that substitute for 21 different frequency, wavelength, and energy ranges that we would normally have to memorize. And then finally, we learned to use this equation, F is equal to V over lambda, to find a frequency from wavelength that allow us to identify what a particular wavelength is.